All right, chemical bonding 2, we're going to talk about these topics in the video. So some exceptions to the octet rule: boron, he only has 5 protons, so it doesn't really have the ability to attract 8. So in this structure, it can only attract 6. So boron is happy with 6. Expanded octets, atoms in periods 3 through 7 can bond with other atoms in a way where they can get more than 8 electrons in their octet. And they're able to do this because their d orbitals are in their outer shells and can accept those electrons. So phosphorus can have an expanded octet because the 3d subshell is very close in energy to the 3p subshell. So phosphorus has 10 bonding electrons around it. 2 of these 10 were promoted to the 3d subshell. All right, sulfur, again, 3d subshell is very close in energy to 3p. So 4 of these electrons were promoted to the 3d subshell. Now xenon, this occurs because the 5d subshell is very close in energy to the 5p subshell. So xenon has 12 electrons around it. 4 of those 12 are promoted to the 5d subshell. And other elements like iodine and chlorine, they can expand their octets in the same way. But it just has to be in rows 3 through 7. Formal charge. So even when you follow the 5 steps for drawing Lewis diagrams, you'll still find that some different arrangements are possible. So for example, they may have different atoms that have the same and the lowest electronegativity value. So who would go in the middle? The formal charges will tell you, it's just a way to tell you what the best structure is. So the formal charges of all atoms in a given structure will always sum to the overall charge of the molecule or the polyatomic ion. And if they don't, then you've made a mistake. So how do we tell which structure is more likely to form? So the more likely Lewis structure will have all formal charges that are 0, or as close to 0 as you can get. If there are negative formal charges, then they need to be on the more electronegative element in your molecule. So here's the formula for calculating formal charge. It's just the number of valence electrons assigned to the neutral atom, and then minus the number of electrons assigned to the atom in the structure. So which one's the most likely structure? The only way to determine this is if you calculate your formal charge. The rule states that the least electronegative element resides in the center, but in this case both elements have the same electronegativity value. So we need to calculate formal charge. So here we go. So here's the valence electrons assigned to nitrogen, chlorine, and then you're going to subtract the electrons that are around it. So around this nitrogen, there's 1, 2, 3, 4, 5, 6, 7 electrons. Around this chlorine, there's 1, 2, 3, 4, 5. Around this chlorine, 1, 2, 3, 4, 5, 6, 7. Around this one, 1, 2, 3, 4, 5, 6, 7. So we've got this -2 charge on nitrogen, so this is a really bad structure. This one is better, so all our formal charges equal 0. All right, which one is going to be the more likely structure? So according to our rules, we could put carbon or sulfur in the middle because they have the same electronegativity value. So we need to calculate formal charge. So again, these aren't very close to 0, so this is not a very likely structure. So let's come up with a better way. So here we could draw it like this. We've got 2 that are 0, a -1 on the more electronegative element, so this one is probably the more likely structure. Okay, so we want to draw the Lewis structure for sulfate and check it using formal charges. So first we're going to add up our valence electrons, so we have 32. Put the least electronegative element in the center and connect terminal atoms to it. Complete the octets. Add up all your electrons that you've used. And now we're going to check our formal charges. Okay. So here we've got the sulfur with a +2, and all the oxygens have a -1. So this is probably not a very good structure. This is better. So since sulfur is in that third row, it can have an expanded octet. And when we allow sulfur to expand its octet and have 1, 2, 4, 6, 8, 10, 12 electrons around it. Look at our formal charges. A lot more zeros, and the negative ones are on the oxygen, and oxygen loves to be negative. So this is a more likely structure. All right, bond energy. So this can be thought of terms in gravitational potential energy. Like a rock on top of a cliff has lots of potential energy. Its potential energy decreases as it falls. The rock's potential energy is at a minimum at the bottom of a cliff. So energy is released during the formation of a bond. Potential energy decreases as the atoms move closer and closer together. Well, the same energy must be added in order to break that bond. Potential energy increases as atoms move farther and farther away from each other. So the amount of energy that is required to break the bond between two specific atoms in a molecule is equal to the amount of energy that is released. Okay, so our bond energy values are in kilojoules per mole. So this really should say per mole. If you break a mole of hydrochloric acid bonds, 432 kilojoules of energy will be absorbed. So when you form those bonds, 432 kilojoules of energy will be released. So remember, these signs tell you it was released or it was absorbed. All right, the graph shows the formation of a covalent bond between two individual hydrogen atoms. And a bond will only form if the energy of the aggregate is lower than the combined energies of the separate atoms. So the energy term is a combination of kinetic energy of the electrons and the potential energy resulting from the proton-electron attractions and the electron-electron, proton-proton repulsions. So as atoms move closer together, the energy decreases. So they're getting closer, energy is decreasing. The kinetic energy of the valence electrons decreases as attraction for the nucleus of the other atom increase, and their motions become more concentrated in the region between the two nuclei. The potential energy decreases as attractions between the nuclei and the valence electrons pull the nuclei closer together. The energy that is lost is released as heat during the formation of the bond. And so the energy that is lost during the formation of the bond is equal to the energy required to break the bond. So at 0.074 nanometers, right here, the bond length of H2, the energy is at its lowest point. So this is where hydrogen, diatomic hydrogen, exists on average. So they can be thought of as springs. So 0.074 nanometers is about an average. As you move further to the left, the bond or the spring is compressed and the potential energy rises. So bond energy, bond length, as the atomic radius of bonding atoms increase, the bond length increases and the bond energy decreases. So here we've got carbon bonding with 3 different halogens. As the radius of a halogen increases, the bond length increases and the bond energy decreases. As the size of the atom increases, the orbital overlap decreases. Okay, so in this course on the AP exam, you will be required to create and use different types of graphical representation. So on this slide, the molecules are represented by space-filling molecules. This model shows differences in the atomic radii of bonded atoms. The problem with this model is that it doesn't show the 3-dimensional positions of the atoms in molecules with more than 4 atoms very well. So which molecule would have the least amount of potential energy? Well, it would be this one because it has the shortest bond. Which bond has the lowest bond energy? This would be the lowest bond energy because it has the longest bond length. As the number of bonds between the atoms increases, the electron density between the atoms increase. For example, triple bonds have greater electron density between the bonding atoms than double bonds, and double bonds have greater electron density between the bonding atoms and single bonds. As the electron density between the atoms increase, the force of attraction between the protons of each nucleus and those centrally located electrons increase. This shortens the bond length. The energy required to break the double bond and the triple bonds is greater because the force of attraction is greater. As you increase the number of bonds between 2 atoms, the energy contained within the bond increases and the distance between the nuclei decrease. The more electrons you put between the two nuclei, the stronger the attraction that those positive nuclei have for the negative electrons. The two nuclei have a stronger attraction for the three shared pairs of electrons than they do for the two shaped pair of electrons. Furthermore, the two nuclei have a stronger attraction for two shared pairs of electrons than they do for one shared pair of electrons. All right, bond order is the number of bonds between two atoms. When the bond order increases, your bond length decreases, potential energy decreases, and the bond energy increase. So you need to know this definition. The more common definition for bond order is associated with molecular orbital theory, and we're just not going to cover that in this AP class. All right, the ball and stick model shows 3D arrangement better than space-filling model. The geometry of these two molecules happen to be 2D, but when we do VESPR, the model does show 3D very well. The weakness here is that the balls are not proportional to the size of the atoms, and the sticks aren't proportional to the bond length and greatly exaggerate bond length. So carbon-carbon bond, in which molecule has the lowest potential energy? It would be the triple bond here. Has the shortest bond length, which has the lowest bond energy. This would have the lowest bond energy because it has the longest bond length. Here's a summary of both molecules, molecular models, and then resonance structure. So we can draw resonance structures between multiple bonds, and so there are Lewis diagrams that are equally valid. When you draw ozone, when you draw the structure, you could place a double bond between the central atom and the atom on the left, or between the central atom and the atom on the right. So which one is it? Well, we would expect the double bond to be shorter than the single bond, but they are both the same length. They both have a length that is about halfway between a single and a double bond. So in fact, there's actually 3 electrons in each bond, not 2 and not 4. And we can't really draw this using Lewis structures. We make one bond single, another bond double. So what we do is we draw resonance structures, and the double arrow, this is the double arrow, means resonance structure. So the ozone, you would draw with resonance structures. So here we go. Here's one for nitrate. So it really exists as a hybrid between all these 3 molecules. You need to be able to determine the effective number of bonds between elements in a structure and use this to explain why the bonds are all the same length. And this is a very common question on the AP exam. If you work out formal charges on the structure, you'll see that the formal charge on nitrogen is +1 and the formal charges on the oxygens are -1. This could be fixed by making a second double bond, but we can't do that because of the valence electrons in nitrogen are only in the second shell, so we can't expand this. Formate, there's only 2 resonance structures here, as there's only 2 places where we can put the double bond. All right, which structure has the shortest bond? Well, it's going to be this one. So the effective bonds between N and O is 1.5, because we have 1, 2, 3, divided by 2. Here we've got 1, 2, 3, 4, divided by 3, 1.33. In some cases, resonance must be used to refine a Lewis structure in order to obtain qualitatively accurate predictions about the effective number of bonds, bond energy, and bond length. All right, try these and we'll discuss them in class.